Another example of projectile motion. So in this case, a projectile is launched. It's going to follow its parabolic trajectory, and then it intersects this object. The set of things that we want to find are capital H is the maximum height when it's at the apex of its motion. Little h is its final height, and the velocity that the object is making right when it hits here. And we're given the initial speed is 42 meters per second, so that's the length of this vector v0, and v0 makes an angle of 60 degrees with respect to the horizontal. And we're also told that the total time of flight, so the total time that the projectile is in the air, is 5.5 seconds. We have no other reason to pick coordinates besides coordinates where x goes to the right and y goes up. And we can assume free fall, so this is just a projectile motion problem. The first thing, I want to split that velocity vector up into its components. So it is initially partly going to the right. So v0, the x part, and at 60 degrees, it's mostly going up. So there's v0, so the initial velocity y component, and there's the initial velocity vector v0, and that is 60 degrees. We can work out the components. I'm going to have the y component is going to be the hypotenuse times sine of 60, and the x component is the hypotenuse times cosine of 60. So let's go ahead and get those written down. So the y component, keeping 3 decimal places while we're working on things, 36.4 meters per second, and then the horizontal component works out to 21 meters per second, because it's a 1√32 right triangle. That horizontal velocity is not going to change because there's no acceleration left or right. The only acceleration that's happening is due to gravity, so objects are accelerating downwards. And so let's go through and try to solve for these unknowns. So the first thing I want to wrestle with is how far, so we're talking about a distance, how far to the top of the parabola. So what's the height at the apex? And in doing that, I'm going to note there's no vertical velocity at the apex, because otherwise it wouldn't be the highest point. So to go through the highest point, you have to go from in these coordinates, a positive vertical velocity to a negative vertical velocity, which means you go through 0. If we use the equation of kinematics that does not involve time, v final squared minus v initial squared, y components, is going to be twice the acceleration along the y direction times that height, h. So we can solve for the height. Also note that at the highest point, our final y y velocity component is 0, so that goes away. So this is going to be minus b0y squared over twice the y component of the acceleration. So I've got a minus 36.4 meters per second squared, and in the denominator I've got 2 times minus 9.81 meter per second squared, and that works out to be 67.6 meters. Okay, so that was a how far, and we have gotten a value for capital H. The next thing that I want to figure out to take the next step in the problem is to ask a how long question. So it's a time question. How long to reaching the top of the parabola? So if the initial height and the final height were the same, this would be completely symmetric, and we could, once I know how long it is to the top, it's also how long it is to the bottom. But I'm beginning and ending at different heights. So it's going to spend more time going up than it does going down. So I need to know how long it takes to get to the apex, and then I know the total time of flight for the projectile is 5.5 seconds. So then I also know how long it takes to go from the apex to its final position. All right, so how long to the top of the parabola? We can use, probably the easiest thing to do is a change in velocity related to acceleration and time. So the final vertical velocity equals the initial vertical velocity plus the acceleration times the time to go up. And again, the vertical velocity of the highest point is 0. So this is going to tell us that time to reach the highest point, so the time up is, move this to the other side, I'm going to have a minus 36.4 meters per second over the acceleration, which is minus 9.81 meters per second squared. So I wind up with a positive value for t up, which is comforting. So it is in fact in the future. All right, so now the total time of flight is 5.5 seconds, and the time to go up is 3.7 seconds, so we can find out how long it takes to fall down. So let me flip over to another sheet of paper for that part. So t, the time of flight, is the time to go up plus the time to fall down. So the time to fall down is going to be the time of flight, 5.5 seconds, minus the time to reach the highest point, 3.7 seconds, is going to be 1.8 seconds. All right, and that's going to be useful. So now we can find little h by asking how far, so another distance question, how far do you fall? And 1.8 seconds starting from rest. All right. So we're going to use kinematics equation of y final minus y initial, and now we're starting at the highest point and falling down to intersect this object. So we're starting our clocks at the highest point, and at the highest point now the initial velocity is 0 vertically. So y component of the initial velocity times t down plus a half acceleration along the y direction, t down squared. And this cleans up a little bit because starting at the highest point, you have no vertical velocity. So that term drops out. So our displacement vertically, y minus y0, I'm going to have a minus sign because we took up to be positive and a sub y is minus 9.81 meters per second squared. So I have a minus a half 9.81 meters per second squared times 1.8 seconds quantity squared, and that works out to be falling minus 15.9 meters. So that tells us that little h is the height of the apex, which was capital H, and it's fallen down 15.9 meters because it fell for only 1.8 seconds. So little h has to be 51.7 meters. So there we have an answer for that. All right. And then the last thing we need to find is what's the final velocity of the projectile. So the final x component of velocity is what it was initially, because there's nothing acting left or right to change that. So it's 21 meters per second. The final y velocity is how fast it's going after accelerating due to gravity for 1.8 seconds. So that's going to be minus 1.8 seconds times 9.81 meters per second squared. And what do we get for that? 1.8, 1.1. Get that to be 17.7 meters per second directed down. All right, so we can write that final velocity, v, as 21 meters per second along the x direction, and then minus 17.7 meters per second along the y direction. And just to practice, we could also write this out as a speed and direction. So the vector, we can give its components in our chosen coordinates, or we can give the magnitude of the vector, which is the speed, times the direction relative to some axis, which is usually the x-axis. All right, so the speed is going to be the magnitude of this vector, so I have the square root of 21 squared plus 17.7 squared, which, if I do that correctly, I get 27.4 meters per second. And then the direction, if you think about this, is going positive x and minus y. So it's in the fourth quadrant. So that is going to be an angle of 40 degrees below the x-axis. So that's minus 40.1 degrees. So our convention is a positive rotation is counterclockwise. So this negative rotation is relative to the x-axis. I go to clockwise 40.1 degrees, or you could write it out in words. It's 40.1 degrees below the x-axis. So we're being really complete here and just practicing things out. But in reality, when asked for a quantity that's a vector, you can just give its components in a particular coordinate system, or you can give a magnitude and a direction. And again, that direction is going to be relative to some axis or some direction, like the horizontal or the vertical. The default in physics is going to be what you take to be the x-axis. So if you don't tell me what it is, that's what I'm going to assume it is. All right. And that is that for that problem. We've answered how high is the apex, how high is a projectile when it crashes in, and then what is its final velocity as a vector.